So we're continuing on with the chapter on probability, right? Chapter 6. So yeah, we're continuing with probability. We're going to talk about sections 6.2 and 6.3. As it's going to turn out, you'll probably kind of see throughout this, all the stuff we did about counting in the previous chapter. Like there's a lot of different things that are quite related when you deal with probability. So basically, this probability chapter is really building on what we did in the counting part of the course. So specifically, now I'm going to show you a way we can use Venn diagrams to solve probability questions. So let E and F be two events for some experiment. And for this problem, the actual experiment isn't going to matter. Okay, so it doesn't really matter how we generate these events, but it's just for some experiment. And suppose that the probability of the event E is 0.4. The probability of F is 0.7. And the probability of the intersection of E and F is 0.3. So now my question is, determine, there's a million different variations I could give you, but we could, let's write, determine the probability of E complement intersect F. Okay, so by the way, in words, like we have to be able to translate mathematical notation to plain English and back, right? That's one of the, because this could have been written in completely plain English without any mathematical symbols, and you have to be able to interpret it. So what this really says is suppose that the probability that E occurs is 0.4, the probability that F occurs is 0.7, and the probability that both E and F occur is 0.3, right? And then you're asked to determine the probability that E doesn't occur and F occurs. Okay. Any questions about this setup at all? Okay. So there are probably multiple ways you can approach this. But one way that's nice because it's nice because well, you can solve the problem and you can also check your answer, is with an Venn diagram. So draw a Venn diagram. So yeah, usually for a Venn diagram, you kind of label it with the number of elements in each region. But this time, we're going to label it with the probability of each region. And also, usually in a Venn diagram, like in the previous chapter, the whole square represents the universe. But now the whole square represents S, the sample space. So the square is, this whole square is S, which is the sample space, or in other words, it's the set of all possible outcomes, right? Okay, so what we're told is that, oh, we're told a bunch of things. Where I'm going to start is, so we're told that the probability of the intersection of E and F is 0.3. So I want to start in the middle here to say, you know, this region has probability 0.3, right? That's the intersection of E and F. Any suggestion for what I should label next? There's multiple options, but what I should label it with? Yeah. Yeah. So just to repeat that, you know, let's arbitrarily, you know, pick, it doesn't really matter if I pick this one or this one. Let's go with this one. We know that in total, this circle should have probability 0.7, right? We've already labeled this with probability 0.3, so this, the remaining part must be 0.4. Similarly, probability of E should be 0.4 in total. We've already labeled this with 0.3, so there's probability 0.1 left over. And as a last step, I want to label my outside region. Can anyone see what that label should be on the outside? Yeah. Okay, sorry. Yeah, 0.2, right? Because we know that the reason this is 0.2 is that all the probabilities should add up to 1, right? And if I add the ones I've done so far, like 0.1, 0.3, 0.4, that adds up to 0.8. So the outside's got to be 0.2. Okay. And now we can answer our question, right? So what's the probability of E not occurring and F occurring? So this is saying we want to kind of take the probability of all the stuff that's not in E and is in F, which should be that region, right? That's everything in F that's not in E. So that would be 0.4. Okay. And I mean, if you really think about it, you probably could have gotten this from just these numbers here, because you could just take 0.7 and subtract 0.3. But this way, you can be pretty certain that you're right, because if you add up all these numbers, you're getting the right values. Like, you know, these add up to 0.4, that adds up to 0.7. You know, everything adds up to 1. So you can be pretty confident that there's no way that your answer is going to be wrong, right? But yeah, any questions about that? Okay. Another slight variation of that. Suppose I tell you that, so this is kind of testing your terminology as well. So if I say, suppose E and F are mutually exclusive events, such that probability of E is 0.5 and probability of F is 0.4. And then you could be asked, what is the probability of E complement intersect F complement? Okay. This is very much the same type of problem, except you're not explicitly told, like, what is the probability of the intersection. You're told that they're mutually exclusive. But we have to remember, mutually exclusive means that their intersection is empty. Okay, so if I draw my Venn diagram now, the intersection, okay, this diagram is almost, it's almost misleading because, I mean, maybe you could, in principle, you could also write this with like 2 disjoint circles if you wanted to. But I'm just going to draw it like normal. And I can just say, well, they're mutually exclusive, so there's nothing in the intersection. The probability of the intersection is just 0, right? Probability of E is 0.5, so I can write a 0.5 here. This is 0.4. And so we see the outside is 0.1. And the outside is, like this is the complement of E intersect the complement of F, right? Because it's the stuff that's not in E and also not in F. So now your answer is 0.1. Okay. So basically, this mutually exclusive thing was used to write the 0 in the middle because they're disjoint. They have nothing in common. So the probability of their intersection is 0. Any questions about any of this? Okay. Actually, that's, I think, everything I wanted to say about 6.2. So now we're into 6.3. So most of the probability problems we're going to look at are problems where you've got a bunch of different possible outcomes, and all of them are equally likely. So think about flipping a coin, right? Heads and tails are equally likely, or rolling a die, all the values are equally likely. So those are, like, I'm not going to say that we always deal with those kinds of problems, because maybe we won't, but most of the problems we deal with in this course for probability deal with equally likely outcomes. So, and when you've got a sample space S with equally likely outcomes, so if the sample space is S, and all outcomes are equally likely, meaning every outcome has the same probability of occurring, then if I have an event E, the probability of E is just the number of elements of E divided by the number of elements of the sample space for every event E. And so this is kind of another way that probability ties in with counting, right? Because basically, if you've got equally likely outcomes, well, then computing a probability of an event boils down to counting the elements of E, so it's counting again, then counting the elements of S and dividing, right? So if you were a little shaky on chapter 5, it's a good time to really review that, because basically, to compute probabilities, we're going to be counting things twice, or counting two different things and dividing. So it's twice as much counting in some sense. Okay, so let's do an example. So pick two cards from a standard deck of cards. Randomly let E be the probability, or sorry, the event that both cards have the same denomination. When I say denomination, I just mean like the number or letter on the card. So I just mean you pick up two twos or two aces or two kings, you know, whatever it is. And so what is the probability of E? Okay. So if you think about it, this is a situation where you've got equally likely outcomes, right? The probability, if I pick just two cards at random, the probability I get the ace of spades and the two of clubs in my hand is the same as the probability that I get the king of hearts and the three of diamonds, right? Or the same as the probability that I get the king of hearts and the king of diamonds. You know, all of these different combinations are all equally likely, right? And here's one thing. It's also, if you think about it, we should think about this as an unordered selection. Because if I get the two of clubs first and the three of spades second, it's kind of the same thing as getting the three of spades first and the two of clubs second. It doesn't affect whether they're the same denomination or not, right? So order really doesn't matter. So I'm going to say that my sample space S is the set of all unordered selections of two cards, meaning it's just all the ways to pick two cards, and I don't care which order I pick them. So, you know, two of clubs, three of diamonds is the same as three of diamonds, two of clubs. So, any ideas how big the sample space is? Yeah. Yeah. Right. All the ways of choosing two cards from a set of size 52. Right. So this is, yeah, bringing us back to our counting stuff. Now, since we're dealing with equally likely outcomes, you know, probability of E is n of E divided by n of S. So I've already computed n of S. I just need to compute n of E. So the question is now, how many ways are there to pick two cards of the same denomination? One thing to remember, so there's 13 different denominations, right? You've got ace, 2, 3, up to 10, and then jack, king, queen, right? And there's 4 suits, right? So 52 cards total. Just in case, yeah. So, okay, so how many ways can I pick 2 cards of the same denomination? Here's how I'm going to think of it. First, I'm going to pick a denomination. There's 13 ways to do that, right? These 13 choices. Maybe I'll call it 13 choose 1, but it doesn't really, it's just 13 anyway. So I've got 13 possible denominations. I choose 1, and then I choose 2 cards from that denomination. Each denomination has 4 cards, so I'm picking 2 of them. So I've got 4 choose 2 choices. So this is for choosing a denomination. So it's kind of a 2-step process. I first pick what the letter or number on the card is going to be, and then this is to choose 2 suits from that denomination. Right, so then at the end of the day, my answer is just, yeah, whatever this is. So, 13 choose 1, 4 choose 2, or 52 choose 2, which I think I wrote down. Maybe I didn't. But yeah, you can count. I think it's, well, I think it's 700 and, no. Do you get, if anyone calculates this, do you get 0.529 roughly? Or, oh, sorry? Okay. 0.588. Yeah, I think I've messed up different things on here. Okay, so, right. Yeah. Hmm. 52 factorial would be pretty big though, because that's 52 factorial is the number of ways to shuffle your cards, like the whole deck, and we're not really using all that information of. Yeah, although you make it, there's something you could do like that. So you could say, okay, I've got. So I think if you kind of take away that factorial thing, so there's 52 choices for the first card. I think this might be kind of along the lines you're thinking. 52 choices for the first card, and then once I've chosen the first card, there's 3 ways to choose the other card to match the denomination. However, this is counting kind of an ordered selection where suppose I pick the ace of spades first. This is saying I pick the ace of spades first and then I pick another ace. But if it came in the other order, it'd be the same. But if you do divide that by 2, that would be okay. So if I kind of take that as my numerator and do 52 choose 2, you'll actually get the same answer as this, as that. So yeah, you are on the right track there. That'll work. But yeah, you have to be careful because you're really doing an ordered selection there. Yeah. Any other questions? Okay. So let's add to this example a little bit. So So what if I wanted to have same denomination or the same suit? Or let's not say same suit, but let's say same color. So there's two colors, right? Red or black. So let's say, what's the probability of having the same denomination or same color, red or black? So now we have to remember this kind of principle of inclusion-exclusion type thing. So this is the same as having the same denomination plus the probability of having the same color. Again, this is picking two cards, right? And then minus the probability of having both. So this one we already computed. It was 13 choose 1, 4 choose 2, or 52 choose 2. Okay. So now the question is, what's the probability of having the same color? And I'll start by saying the denominator is going to be 52 choose 2. But then the question is, what's the numerator? How many ways can you pick two? How many different ways are there to do an unordered selection of two cards of the same color? Yeah. That's like the most of it. And then there's one little bit extra because you also have the choice of which color you're picking. So this is picking, you have two choices of color, red or black. So you have to pick one of those colors. But then once you pick the color, the 26 choose 2 is the right thing. Because once you pick a color, I've got 26 of that color. I pick 2 of them. Okay, and then we need to do, how many ways can I pick the same denomination and the same color? This is the easy part, right? The denominator. So the way I'll think about this is, again, I'm going to pick a denomination, and then I'm going to pick a color. And then if you think about it, if I pick, let's say I pick aces, and then I pick red, there's only 2 red aces, right? So I don't really need any other thing, but I'll just write this 2 choose 2, even though 2 choose 2 is just equal to 1. But yeah, this is like pick a denomination, pick a color, and then there are 2 things of that color, and I'm choosing 2 of them. So there's 2 choose 2 ways to do that, which is 1. And I think if you calculate this, unless I've messed up my notes here, it's something like 702 over 1326, which apparently reduces to 9 over 17, which is roughly 0.529. I think. On a test, usually it's going to be okay to write things in decimal form unless we really ask you not to, but usually that should be okay. By the way, one thing I wanted to mention, like on your calculator, is so you don't have to be able to do this in your head to reduce fractions. I'm pretty sure there's a button for this. So there's some sort of A divide B button or something, or maybe it's capital A divide capital B, I'm not sure, but if you use somewhere on the calculator, there should be like some kind of A divides B button, which is good for reducing fractions. So that might be a good thing to learn. Is it little a divided little b, or what's the? Oh, sorry. Yeah. Okay, well, yeah. Anyway, there's some kind of button that does it. So, sorry. Oh, okay, I see. Yeah. Yeah, I'm not that, I haven't really used this calculator myself, but okay. Yeah. Okay, let's keep doing a few more examples. So one thing, so you remember when we were doing counting, there's this thing that I said that, sometimes if you've got a really complicated counting problem, it's easier to count the complement and then subtract. There's a very similar thing with probability. And so the idea is, for any event, the probability of the complement of E is 1 minus the probability of E. You can interpret this as saying the probability that an event doesn't happen is 1 minus the probability that it does happen. So if the chance of rain is 80%, the chance of not rain is 20%, right? Okay. So as an example, suppose you've got a bag contains 10 red balls and 90 black balls. Remove 5 balls without replacement, which means we take them out kind of one by one, put them on the table. You don't take one out, put it back, take one out, put it back. You just take 5 out. So first, what is the probability? Exactly 2 red balls are selected. Okay, so I'm going to think about this like, again, you should think of it as an unordered selection. If I'm going to think of it as I don't really care what order I take the balls out. So if it's like, yeah. If it's black, 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 red, red, I don't really care, if I take them in that particular order, or if I take red, red, black, black, black. So I want to think of it as my my sample space is the set of all unordered selections of 5 balls. So the size of the sample space is 100 choose 5. Got 100 balls. I'm going to pick 5 of them. So let E be the event that exactly 2 red are chosen So, any thoughts about how many elements E has? So how many ways can you pick exactly 2 reds? Oh, sorry. I see where you're getting, maybe I see where you're getting that, but yeah, no, it's not quite what we want. Any other thoughts? Yeah. Yeah, that's great. So, because I've got 10 red balls in there, so, and I'm picking 2 of them. There's 10 choose 2 ways to do that. You then have to remember, I think one easy mistake to make is to stop at this point and say, oh, pick exactly 2 red balls. But picking 2 red balls is not really what my sample space is talking about. I'm supposed to be picking 5 balls in total. So just as you said, you know, you want to pick 2 reds, and then you want to, after that, pick 3 blacks, right? And that's going to give me a selection of 5 balls, which, you know, makes sense for my sample space. So then probability V is just 10 choose 2, 90 choose 3, over 100 choose 5. Okay, which is about this doesn't seem right, but do you get this? It can't be right, can it? Anyway, it's something. If you reduce the fraction, if you compute the fraction. Okay. Now, next thing, what if we want to say, what's the probability that there's at least 1 red chosen? Okay. Now, there's 2 natural ways of doing this, but one's going to be way quicker than the other. One way you could do this is say, okay, well, compute the probability of getting exactly 1 red plus exactly 2 reds, 3 reds, 4 reds, 5 reds, right? And then add those all up and you'll get the right answer. But if you think about it, getting at least 1 red is the complement of getting 0 reds, right? And that's going to be faster to count. So I'll take 1 minus the probability that you have 0 reds. Which is 1 minus the so the probability of getting 0 reds is 100. Again, you got 100 choose 5 on the denominator. And your numerator is just going to be 90 choose 5. Right? Because, yeah, you're picking everything from the blacks. Right? So this shows you how this rule of complements can be useful. You know, if it's easier to count the complement, then you should count the complement. Any questions about that? Oh, okay. Yeah. I had written in my notes like 0.7, but yeah, somehow I was missing a zero there. So what if I now flip a coin six times? Okay, so find the probability. So let's say for part A, that it lands on heads. Exactly 3 times. Okay. Okay. So how big is my sample space? Flipping a coin 6 times. Yeah. Yeah. Right, because that's how many outcomes there are. And again, this is kind of connecting back to something a while ago, but like, you got to be very careful. Yeah, flipping a coin only has 2 outcomes, but flipping a coin 6 times has 2 to the 6. So your sample space is not 2, it's 2 to the 6. How many different ways can it land on heads 3 times? So what's the size of this event? So outcomes where it lands on heads 3 times. It's going to involve a 6, for sure. 6 choose 3, yeah. Right, because basically you got 6 positions and you're picking 3 of them to be heads and the other 3 are tails. Yeah, so it really it exactly boils down to 2 different counting problems, and then that's your answer. Divide them. Okay, so now if I say, let's say at most 3 heads. Okay. So this time you could try to count the complement or something, but it's only going to help you a little bit. So let's just count this directly. And this is going to be pretty similar. It's the probability you have 0 heads. So everything's divided by 2 to the 6. Probability of 0 heads, 1 head, 2 heads, or 3 heads. Which is apparently 42 over 64, which is roughly, or maybe it's exactly 0.65625. Okay, so about 65 or 66% of the time, you'll have at most 3 heads. What's the probability that the first and last flips are heads? So out of 6 flips. I'll do the first step. Again, dividing by 2 to the 6. What's the top going to be? The numerator? Any thoughts? Yeah. Oh, not really. I guess all of these ones we're kind of thinking them as order because we're kind of recording the first head or the first flip, the second flip, the third flip. So, but Any thoughts about, yeah? So this one's going to be easier than that. So if I kind of lock in and I say, okay, the first one's head is a heads, the last one's a heads, then if you think about it, for each of the interior, like the second, the third, the fourth, and the fifth flips, there's two choices for each of them. So yeah, it does just boil down to 2 times 2 times 2 times 2. So there's that many ways to flip a coin 6 times, such that the first one's a heads and the last one's a heads. And that just boils down to 1/4. Which kind of makes sense that it's 1/4 because the probability the first one's ahead is a half. The probability the last one's ahead is a half. So like, and if we're kind of ignoring all of these ones, you would think it should be about 1/4, right? Because yeah. But formally, that's how you can compute it.